Okay, Assalamualaikum warahmatullahi wabarakatuh dan selamat sejahtera. Sebelum kita mulakan majlis Kolokium pada petang ini, Al-Fatihah. Jadi pembentang pada petang ni ialah Dr. Amirah binti Muhammad Saha. Latar belakang pendidikan beliau tahun 2009 Skudai, Bachelor of Science Matematik, Skudai UTM Skudai, UTM Skudai. Seterusnya tahun 2011 Master of Science dalam Mathematical Engineering juga di UTM Skudai. Dan 2020 Doctor of Philosophy, Brunel University London. Tajuk pembentangan beliau pada petang ini, Computational Fluid Dynamics of Single and Two-Phase Flow in Microchannels. Jadi untuk mengetahui dengan lebih lanjut berkenaan pembentangan beliau, jadi saya tanpa melengahkan masa lagi mempersilakan Dr. Amirah untuk membuat pembentangan. Dipersilakan Dr. Amirah.
Okay, Assalamualaikum semua. Terima kasih Dr. Agus because giving this opportunity to share with the others about my study, my project during my PhD study. Okay, so start sharing. So everybody can see my slide?
Yeah, clear.
Okay. Okay, Assalamualaikum. Okay, so my name is Amirah Muhammad Saha. I just joined FSKM last April. Okay, so for today, I'm glad to share my research during my PhD at Brunel University. And also I did, due to the certain circumstances, I did finish my study at UNIMAP, University Metropolis. So the title for my research PhD is Computational Fluid Dynamics of Single and Two-Phase Flow in Microchannel. Okay, so I did this research under the two-phase flow heat transfer group, which is here is a group leader, also my main supervisor, and Dr. Jan, Professor Tassos Perianis, and also Dr. Jan Wizing as a co-supervisors. Also working with two visiting researcher, which is Dr. Muhammad from the Zagazig University, Egypt, and Professor Ikhlas Muhammad at the University of Technology, Baghdad, Iraq. And also this is a group member and also the PhD student under this research group, which is Dr. Javani and also Dr. Mimanto. So Dr. Mimanto is the one who doing the experimental study, but in this group, I the only one to do the numerical work, which is assimilation work. Okay. Okay, so here is some research background about my study. Okay, so which is the concept of the heat removals by liquid flow in the microchannels was introduced by these two guys, Tukiman and Peace, early 80 for the electronic cooling, which is they demonstrate that the heat removal rates of 0.79 kilowatt per centimeter squared by using a single phase flow. Okay, so basically in microchannels, they characterize the microchannels by the diameters of the channels, which we call the hydraulic diameter. Okay, so most of the study are using these two characterized based on the application, which is from the handle the range is between 1 to 100 micrometer, and from the current data is between 10 to 200 micrometers. So in microchannels, the application is mostly for heat exchangers and microreactors, lab on chip, microelectronics, and also microelectromechanical system. Okay, so the motivation of this study is we found that there are discrepancies report in the previous study. So basically it's due to the measurement uncertainties and also the scaling effect, because of most of the study nowadays is still using the conventional theory, which is a micro-scale theory, but which is applicable to the micro channel system. And in a multi-channel configuration, there are limitations of the study only focus on the single cells without considering the flow distribution. So we found that this lead to the unders and or over predictions of the microchannel heat sink performance and also inconsistent results in the open literature. Okay, so we know that the understanding of the flow characteristics is quite important. Basically, this have the significant influence in a geometrical structures of the manifolds, which is played an important role in the flow university distribution. And however, in experimental study, they have a limitation to extract the localized flow and temperature data, which is this is very important to characterize the fluid flow and the heat transfer. Okay, so for the two-phase flow issues is we found that the inconsistencies in terminology of the flow pattern in two-phase flow, and also there are still limits few works which is deal in numericals mentioned for the gas and liquid flow regime in microchannel. And also for the specific flow pattern, which is in a slug flow, to only limit for the most of the numerical study that conduct in previous study only use the assumption of the dimensional asymmetric study, which is because of they want to reduce the computational time, but this lead to the identical bubble slug. Okay, so the shape of the bubble will be the same. However, we know that the process of the bubble generations by using the asymmetric assumption is not acceptable. And also, we have the appearance of the real dry out in a microchannel system in numerical simulation is still needed. Okay, so here is the objective in my PhD study, which is I have about six of them, which is I have to do in a single phase flow and also two-phase flow, which is in a single phase flow, have to simulate the single channel configuration or also multi-channel configuration. Okay, so in the single channel configurations, I just focus on compare the numerical results with the standard theory and also the correlations, and also assessing the effect of the size on the fluid flow and heat transfer. And also to examine the effect of the conjugate heat transfer in a microchannel system. However, for the microchannel configuration, we just focus on study on the flow distributions, which is we examine the geometrical effects such as for the manifold shapes, the number of channels, the inlet flow arrangement. Okay, so in two-phase flow, which is this is the third project, which is they have the two objectives, which is have to study the flow pattern map of the adiabatic two-phase flow in circular microchannels, and also the study of the fluid flow and the heat transfer of the slug in a circular microchannel without phase change. Okay, so I'm doing the fully simulation. I'm doing the NSTIS fluent to simulate all the works and the numerical work, and also I construct the geometry and the meshing by using NSTIS ISAM. Okay, so here is the computational domain. Okay, as you can here is a schematic of water experimental facilities. So here is the facilities. So this is the microchannel test section that I have to simulate. Okay, so in order to assess the size effect, I only for using the 3D thin wall computational domain because we want to reduce the computational time. However, in order to study the conjugate effect, I have to simulate the whole test section, which is considered the copper block. So here is the channels on the top of it, and here is the copper block. You also can see from here. All right. Okay, so what as a result, which is here is some of the research contribution. Okay, so we managed to see the effect of the entrance length because of most of the experimental, the way they to get the data reduction, they just assume that the velocity profile, which is entered at the inlet of the channel, which is this is the plenum, and here is the channel here. So they just assume that the velocity profile is uniformly distributed, which is we assume that is a fully developed. However, as the advantages by using the CFD, we can plot, we can get the velocity profile at a certain location that we want. For example, here, because we can see that the velocity profile at the inlet of the channel is not fully developed compared to the along the channel, compared to the other location along the channel. This is because we also can show graphically by using ANSYS rules, CFD, which is we can see this is the velocity profile happened because of we got the vena contracta phenomena happen at the inlet of the channel, which is this is produced by the sharp edges corner at exactly at the inlet of the section. All right, so here you can see also the velocity contour and the streamline at the inlet of this channel. Okay, so which is this result is successfully published at Applied Thermal Engineering. Okay, so the second objective is this is another objective for the first project, because we also managed to show that the effect of the conjugate heat in a microchannel system is significant. Okay, so in my study, I did for this case I did a 4 model, which is I have a 2D thin wall model, because I have to conduct this study because I need to compare with the conventional theory, because in a conventional theory they're just using a 2-dimensional model. All right, and also I do 3D thin wall, which is in a 3D thin wall. The assumption that you use in experimental is exactly the same that we did in a simulation, which is in terms of the boundary condition. Okay, so in order to study the effect of the conjugate, what I have to do is I am doing a 3D full conjugate, which is you have to simulate the whole test section with a copper block. All right, so what we found that for the 3-dimensional, which is exactly the experimental data, we are in agreement with the experimental data provided by the provided by the group in my research. Okay, so because of we know that we get a similar result because of the assumption is exactly the same using in experimental. However, we can see the effect of the conjugate was significant when you can see the percentage difference in the percentage difference by using the 3D full conjugate is more than 50%, which is you can see is not agree with the experimental data, and also by the 3D thin wall. Okay, so this is because we found that in experiment they assume that the heat flux is uniformly distributed along the channel. All right, so however we managed to show that they have a conjugate effect in a microchannel system, which is we can see there are reduction of a heat flux along the channel. That's why we get a lower Nusselt number compared to the predicted, which is my simulation in a 3D thin wall without considering the conjugate effect, and also with the real data, which is the experimental data. So you can see also in a 3D dimensional, you can see that the Nusselt number is uniformly distributed. However, if we consider they have a conjugate effect, which is we simulate the whole test section, we can say that the heat flux is not uniformly distributed. Okay, so this one is also published in the same paper. Okay, other than that, for this, I have some result, which is this is the objective of assess the size effect. Okay, so in the size effect, I just show for the effect of the aspect ratio. Okay, so based on the friction factor against the aspect ratio, we can say that it's decreasing when the aspect ratio is increasing. Okay, so basically this one this is happen because of the velocity profile at the different or the various size of the channel have a significant influence also. That's why we can see a significant effect of the aspect ratio in this microchannel heatsink system. Okay, so we also, the advantages of this FD, we can also provide the graphical plotted, which is, you can see the velocity, and this is the velocity profile, and this is the temperature profile. You can see the slightly different between the lower aspect ratio and the higher aspect ratio here. So that's why we got a different different fluid flow and also the temperature behavior when we varies the size of the channel. Okay, so here is a functional domain for my second project, which is I deal with the multiple configuration. Okay, so here is the detail of the taxation, which is used in the experimental, because in the previous study, we know that the effect of the conjugate is significant. So that's why we have to simulate the whole taxation here, considering the coupler block. And also, we know that the importance of the structure of the manifold. So we include in a computational, our computational domain. Okay. Okay, so one of the contribution, because in this study I study about the flow distribution for the different shape of the manifold, the different number of the channels, and also a difference of the inlet configuration, but I'm not showing here. But the last thing what we found that we found that they have a significant influence of the separation flow, which is this one is the occurrence at the sharp edges of the manifold. Okay, so in order to reduce this occurrence, which is we believe that this occurrence will affect the non-distribution in among the channel. So we try to reduce the sharp edges here. Okay, so in order to determine whether we get a better uniformity of the flow distribution inside the microchannel, so we calculate the maldistribution factor. Okay, so we can see here that the maldistribution factor reduced about almost 15%, which is the lesser of the maldistribution factor value, which means the flow distribution is better compared to the other design, which is I have compared my study between a trapezoid manifold and also the rectangular manifold. All right. Okay, so the last project, which is the third project. In the third project, I'm doing two-phase flow. Okay, so in two-phase flow, here is a numerical flow pattern map of the R134A. Here is the refrigerant that we use in this system. Okay, so here the blue and the red one is a numerical work. Okay, so we compare with the provided from the previous study, which is from the Chen, Tian, and Karanis flow pattern. Okay, so based on this comparison, we found we are in agreement with the provided flow pattern. However, due to the limitation of the model, because to provide the numerical flow pattern, I'll just use two-dimensional asymmetric, because I need to reduce the computational time. Okay, so as you can see here, the Chen flow pattern with the chaotic behavior provided by Chen is not observed at our numerical work, because of in numerical work we only observe the large amplitude wave liquid film. However, this result is still in agreement. Also, we compare the correlation that provided by them. Okay, so I plotted all the flow pattern based. This plotted data is based on the information that I showed to you before. Okay, so it's almost agree with the correlation. Just there are some of bubble flow pattern happen and the slug flow pattern. However, this is still acceptable because of we can see that in the previous study they have a lots of terminology between the bubble flow and also the slug flow. And also we can see that for the chain flow is observed more early compared to the provided correlation. Okay. Okay, so the last objective in this project, which is I'm doing a three-dimensional simulation for the slug flow pattern specifically. Okay, because we know most of the study just conduct in two-dimensionals, which is this one is lead to the similar shape of the bubble flow, which is I can show to you what the meaning by the similar shape. Okay, so here the meaning by if you doing our simulation in two-dimensional asymmetric dimensional domain, we can get only similar shape of the bubble. However, if we conduct in a three-dimensional simulation, we can see the bubble shape along the channel is not identical. Okay, so when you as you can see here, we have the dry zone bubble shape, and also we have the irregular shape of a bubble slug. And here is what I can say the bullet shape, which is a perfect shape for the slug flow. All right. Okay, so the meaning of doing this study, because of we know that different shape of the bubble will having a different velocity profile and temperature profile. So here is some example, which is we study in detail the velocity profile occur exactly at the location of the bubble, which is this is the tail and this is the front of the shape. Okay, so we plotted the velocity profile and also the temperature profile exactly the exact location that we want. All right, so because we believe that as you can see here, different different shape of the bubble will lead to the different behavior of the temperature and also the velocity profile. So we can see for the bubble with having the dry out region have a higher temperature wall temperature profile, which is at here this bubble, these 5 bubble having the dry out, so they have the peak of the wall temperature. Okay, so here is the fluid temperature. All right. Okay, so in terms of the study, the heat transfer rate, we are calculate the Nusselt number. Okay, so for the dry out region, we know we can see that it will lead to the lower heat transfer. Okay, so that's why this study conducting the 3D dimensional is very important, because of we have to study in detail the behavior of the fluid flow and also the heat transfer. Okay, all right. So what I can say in general, the research in my study, the main research contribution is we can say that the 3D full conjugate simulation can help in determining how much is the error due to the assumption of the new uniform heat flux. And also in order to reduce the flow recirculation and to improve the flow distribution, we propose a newly design of the inlet manifold with the smooth edges. And also we can say that a non-identical shape of the gas bubbles was observed in 3-dimensional study. And also this led to the variation of the wall temperature behavior and also effect on the heat transfer rate. Okay, so as a conclusion, that the conjugate simulation needs to be carried out to accurately predict the microchannel heat transfer rate, and a newly designed proposed in order to reduce the occurrence of the flow recirculation in inlet manifold, and also to improve the flow distribution over the channels. And we know that the study show that CFD can be used to obtain the realistic two-phase flow pattern maps, and also the dry out that occur at the rear or the tail of the bubble slat minimize the heat transfer rate due to the high wall temperature. Okay, so here is some articles and publication and also the conference that I joined. Okay, thank you.
Okay, terima kasih Dr. Amirah. Okey, sekarang sesi soal jawab. Saya buka untuk para pensyarah bertanya soalan. Dipersilakan kepada pensyarah yang nak bertanya.
Assalamualaikum warahmatullahi wabarakatuh, Doktor.
Salam Dr. Zaimah.
Okay, very impressive research. What can I say is Dr. Amirah did a lot of many objectives, and all the objectives are achieved, right?
Alhamdulillah.
Tanya Doktor.
Thank you.
Doktor, all may I know all the attractive findings, kan, very colorful findings, kan. All the results do you obtain from CFD Fluent software?
Yes, all the result is we can extract from the ANSYS Fluent.
Oh, ANSYS Fluent.
ANSYS Fluent, yes. We can extract all the results from them, from that solution.
And may I know about in terms of the equations that you apply to generate the results?
Okay,
so I do not see.
Oh, okay. So basically, there's no other equation that I input in the ANSYS Fluent, but in ANSYS Fluent, if you have you have some added equation to solve your work. So basically, you can use UDF, which is you can put inside the ANSYS Fluent, which is you have to give the information inside the ANSYS Fluent. But I don't have any experience with that yet, because due to because I have the lots
so it means
of
that so it means that you do not play with the equations.
No, I didn't insert any equation there. I just use the equation that provided in software. Yes,
software.
Exactly.
Okay. And then we modify according to our specific research that design yang Dr. Amirah kata design tadi tu kan. Oh, so
exactly. Yes, exactly. But it's manageable, and for me, I think it's easy to put the equation inside. But yeah, it's something good to do.
Yes. InsyaAllah lepas ni postdoc ke apa ni Doktor? Okay.
InsyaAllah.
Terima kasih Dr. Amirah. Terima kasih Dr. Agus.
Thanks for asking, Dr. Go.
Okay, terima kasih Dr. Zaimah. Lagi siapa yang bidang fluid dynamics? Saya rasa ramai kat fakulti kita, kat department kita yang bidang fluid dynamics ni. Selain daripada Dr. Zaimah, siapa lagi boleh ni? Silakan bertanya. Tidak ada banyak masa lagi. Ada soalan, silakan. Fluid dynamics, siapa lagi? Fluid dynamics. Biasanya bidang ni kalau kita apply kat mana, Dr. Amirah?
Bidang ni, normally maksudnya application dia.
Yeah.
Semua kepada kita punya application semua kepada cooling thermal system lah. So this study we can manage ataupun dalam application in really dalam microchip ataupun any electronic micro device ataupun even bigger than that also dalam battery system, we can use this. Tapi dalam projek saya, I just focus with the micro channel heat sinks lah.
Any more question, please?
Maybe because of my area is basically boleh dikatakan mostly in mechanical engineering part lah kot mungkin.
Dr. Hazwani ada tak yang bertanya melalui YouTube, Dr. Hazwani? Pensyarah cawangan, kalau ada yang bertanya melalui YouTube, jika ada soalan daripada chatting box, mungkin tak ada.
Tak ada soalan di chatting box.
Okey, kalau tidak ada apa-apa, ada tak isu-isu lain berkaitan Kolokium? Kalau ada nak dibangkitkan semua pensyarah di sini, beri cadangan dan sebagainya. Okeylah, jika tiada apa-apa isu untuk dibangkitkan, kita tangguhkan Kolokium kali ini dengan surah Al-As dan tasbih kafarah.